Good day viewers, we shall start with some don'ts about matrix algebra. Note that we have defined addition and multiplication of matrices. These operations are not behaving exactly as the way algebra or arithmetic of real and complex numbers go. So, one has to be little more vigilant and should not be misguided by analogy while one is manipulating matrices. Unlike in real or complex numbers, it is not true in general that AB is equal to BA. For example, let A be the matrix 1, 2, 3, 4 and B equal to 5, 6, 7, 8. Then AB will be equal to 1, 2, 3, 4, 5, 6, 7, 8, which is equal to while BA will be equal to 5, 6, 7, 8, 1, 2, 3, 4, which is equal to clearly, it follows that in general AB is not equal to BA. Unlike in real or complex numbers, it may happen that AB equal to 0, but neither A is equal to 0 nor B equal to 0. Example, let A equal to 3, 2, 6, 4 and B equal to 2, minus 4, minus 3, 6. Then A is not equal to 0, also B is not equal to 0, but AB, which is equal to 6 minus 6 minus 12 plus 12, 12 minus 12 minus 24 plus 24, which is equal to 0, 0, 0, 0. The law of cancellation is not valid here. That is, one cannot conclude C equal to D from AC equal to AD. Example, suppose A equal to 1, 1, 1, 1, C equal to 1, 2, 3, 4 and D is equal to 3, 4, 1, 2. Then AC equal to 1 plus 3, 2 plus 4, 1 plus 3, 2 plus 4, while AD is equal to 3 plus 1, 4 plus 2, 3 plus 1, 4 plus 2. Thus, AC equal to AD, however, C is not equal to D. We will now talk about determinant, adjoint and inverse of a matrix. Determinant of a square matrix is one of the very important concepts related to matrices. It is a single number derived from a given square matrix, which is useful at number of situations in mathematics and its application. It can be defined in many ways. One of these definitions is inductive definition. The phrase inductive definition is a technical word, but it roughly means that you are able to give appropriate definition for initial case, then after one is able to describe the procedure of moving to the next case from the current one. If this is done, one accepts that the definition is valid for all the positive integers or for all positive integers starting from the initial case. Determinant of a 1 by 1 matrix A equal to matrix A is the number A itself. Determinant of a 2 by 2 matrix A equal to ABCD is the number AD minus BC, that is, the product of the entries on a main diagonal minus the product of entries on the other diagonal. The determinant of a matrix A is denoted by mod A. Thus, we write mod A equal to AB CD, which is equal to AD minus DC. The determinant of a 3 by 3 matrix A equal to A11, A12, A13, A21, A22, A23, A31, A32, A33 is defined in terms of determinants of 2 by 2 matrices. The definition is the determinant of A equal to A11, A22, A23, A32, A33 determinant minus A12 into determinant A21, A23, A31, A33 plus A13 into determinant A21, A22, A31, A32. Therefore, determinant A is equal to A11, A22, A33 plus A12, A31, A23 plus A13, A21, A32 minus A11, A32, A23 minus A12, A21, A33 minus A13, A31, A22. In the next example, we shall soon see that there is a nice way to write down this expression in a way which can be easily applied and remembered. In general, the determinant of a n by n square matrix A equal to Aij is defined by determinant A equal to summation I equal to 1 to n Aij into Cij for any fixed j, where Cij is the cofactor of Aij defined by Cij equal to -1 to the power I plus j into Mij, where Mij is the minor of the matrix A, that is the determinant of the n minus 1 by n minus 1 matrix found by suppressing ith row and jth column of matrix A. Note that it can be found by fixing any j. Surprisingly, all these values are same. The formula determinant of A equal to j equal to 1 to n Aij Cij for any fixed I also can be used by fixing any I. Again, surprisingly, all these values are same. The determinant of the 0 matrix is 0 and the determinant of the identity matrix is 1. We shall find the determinant of a 3 by 3 matrix using both equivalent forms. Example, we shall find determinant of A equal to determinant of 1, 2, 3, 4, 5, 6, 7, 8, 9. First form, we write down determinant equal to 1 multiplied by 5 multiplied by 9 plus 2 multiplied by 6 multiplied by 7 plus 3 multiplied by 4 multiplied by 8 minus 3 multiplied by 5 multiplied by 7 minus 1 multiplied by 6 multiplied by 8 minus 2 multiplied by 4 multiplied by 9, which is equal to 225 minus 225, which is equal to 0. Second form, here let us fix I equal to 2, so that our formula for this case is determinant A equal to summation j equal to 1 to 3 A to j C to j, that is equal to A21 into C21 plus A22 into C22 plus A23 into C23. Therefore, determinant A is equal to 4 multiplied by negative of the determinant 2, 3, 8, 9 plus 5 multiplied by the determinant 1, 3, 7, 9 plus 6 multiplied by the negative of the determinant 1, 2, 7, 8, which is equal to 4 multiplied by 6 plus 5 multiplied by minus 12 plus 6 multiplied by 6, which is 0. Now, we will look at some properties of determinant. 1. The value of the determinant remains unaltered if rows and columns are transposed, that is, determinant of A is equal to determinant of A transpose. 2. The value of the determinant is multiplied by the constant lambda if each element of the row or column is multiplied by lambda. 3. The determinant has a 0 value if 2 rows or 2 columns are linearly dependent. If elements of one row or column of a determinant are the sum of 2 numbers, then the natural law of addition holds, as for example, determinant of A11 plus B11, A12 plus B12 up to A1n plus B1n, so on. The last row is AN1, AN2 up to ANn. That will be equal to determinant of A11, A12 up to A1n up to AN1, AN2, ANn plus determinant of B11, B12 up to B1n, and the last row is AN1, AN2 up to ANn. If one uses the properties number 3 and 4, one gets 5. The value of the determinant remains unaltered if a multiple of one row or column is added to corresponding elements of some other row or column. 6. Determinant of the product of two matrices is the product of the determinant of these matrices, that is, determinant AB is equal to determinant of A multiplied by determinant of B. Adjoint of a matrix. Adjoint of a n by n square matrix A equal to Aij is defined and denoted by adjoint A equal to Cij transpose, where Cij is equal to -1 to the power I plus j multiplied by Mij, and Mij is the minor, that is the determinant of n minus 1 by n minus 1 matrix obtained by suppressing the ith row and jth column of A equal to Aij. Example: find adjoint of the matrix 1, 2, 3, 4, 5, 6, 7, 8, 9. From our definition, it will be adjoint of a matrix 1, 2, 3, 4, 5, 6, 7, 8, 9 will be the matrix having the entries as the determinants as shown, which is equal to the matrix -3, 6, -3, 6, -12, 6, -3, 6, -3. Now, we will look at the inverse of a matrix. Inverse of a n by n square matrix A is another square matrix B such that AB is equal to BA is equal to I. It is not necessary that such a matrix B exists. If it exists, it is denoted by A inverse, and in this case we say that matrix A is invertible. Thus, when A is invertible, we have A inverse equal to A inverse A equal to I. It is clear from this that determinant of A inverse equal to determinant of I, which is 1. Therefore, determinant of A multiplied by determinant of A inverse is equal to 1, from which it follows that determinant of A and determinant of A inverse both are non-zero. In fact, A is invertible if and only if the determinant of A that is mod A is non-zero. When determinant A is non-zero, the matrix A is also called non-singular matrix. Thus, A is invertible if and only if determinant A is non-zero, if and only if A is non-singular. If A is non-singular, it is invertible and its inverse can be found by A inverse is equal to 1 divided by determinant of A multiplied by adjoint of A. Example, if A is equal to 1, 2, 3, 4, then A inverse, which is equal to 1 over determinant of A into adjoint of A, will be equal to A inverse equal to 1 upon minus 2 adjoint of 1, 2, 3, 4, which is equal to 1 upon minus 2 into the transpose of the matrix 4 minus 3 minus 2 1, which is equal to 1 upon minus 2 4 minus 2 minus 3 1, which is equal to minus 2 1 3 and a half minus 1 half. Rank of a matrix. Suppose A equal to Aij is a m by n matrix. We define the row rank of A as the maximum number of linearly independent row vectors of Aij. Similarly, column rank of A is the maximum number of linearly independent column vectors of A. It can be proved that for any matrix A, the row rank and the column rank of A are equal. This common number is called the rank of A, and we shall denote it by rank A. It is clear that rank of A should be less than or equal to minimum of m and n. We have seen that there is a link between determinant and linear independence. So, we have another equivalent definition of a rank of a matrix. The rank of a matrix is the maximum order of a non-vanishing determinant that can be formed out of the given matrix. As both these definitions are equivalent, rank found using any of the definition will be equal. So, as per our convenience, we can use any definition. Example, we shall find the rank of the 2 by 3 matrix using both definitions. Here A equal to 2, 3, 8, 4, 6, 16. First method. We first note that rank of A is less than or equal to minimum of 2 and 3, which is equal to 2. Our second observation is that the two row vectors 2, 3, 8 and 4, 6, 16 are linearly dependent, as 2 multiplied to 2, 3, 8 minus 1 multiplied by 4, 6, 16 is equal to 0, which is a non-trivial linear combination of 2, 3, 8 and 4, 6, 16 that is equal to a 0 vector. This means that we cannot have two linearly independent row vectors. On the other hand, we do have one vector which is linearly independent. Thus, row rank of A is 1. To find column rank, we start with the observation that the set of column vectors, the set consisting of 2, 4, 3, 6, 8, 16 is linearly dependent, as 3 multiplied by 2, 4 minus 2 multiplied to 3, 6 plus 0 multiplied to 8, 16 is equal to 0, is a non-trivial linear combination which is 0. Next, we have to see if we can find two vectors out of these 3 which form a linearly independent set. But that also is not possible, as we see all these 3 combinations of 3 vectors, chosen 2 out of them is giving the non trivial linear combination equal to 0. Thus, none of the two column vectors give us a linearly independent set. Note that here each of the singleton set of the column vectors is linearly independent. Thus, the maximum number of linearly independent column vectors here is 1. Hence, the column rank also is 1, which was expected. Second method. In the second method, we just have to observe that all 2 by 2 subdeterminants here are 0. That is, the determinant 2, 3, 4, 6 is same as determinant 3, 8, 6, 16 is same as determinant 2, 8, 4, 16, which is equal to 0. Thus, the maximum order of non-vanishing subdeterminant here is 1. Hence, the rank of the given matrix A is 1. Solutions to simultaneous linear equations. We started our discussion of matrices and vectors primarily with an objective of solving simultaneous linear equations. Now, we are in a position of carrying out the discussion. We say that a system of equations is inconsistent if there is no common solution for the given system. If there is a common solution, unique or many, we say that the given system is consistent. Henceforth, by a solution of the system, we shall always mean the common solution, which satisfies all the equations under consideration. Example: 2x plus 3y equal to 6 and 4x plus 6y equal to 9. This system is inconsistent, as if there is a common solution xy, then the second equation can be written as 2 into 2x plus 3y equal to 9. But because of the first equation, we get absurd and untenable identity 2 into 6 is equal to 9. Hence, there is no solution for the system. Therefore, the system is inconsistent. Geometrically, these equations represent two parallel lines in the xy plane, and hence there is no common solution. Example: 2x plus 3y equal to 6 and x plus y equal to 9. This system of linear equations is consistent, as we can find the solution by substituting the value of y from the second equation into the first equation. One gets 2x plus 3 into 9 minus x equal to 6. Therefore, 2x plus 27 minus 3x equal to 6, and therefore, minus x equal to minus 21. Therefore, x equal to 21, and from the second equation one gets y equal to minus 12. Check that xy is equal to 21 minus 12 satisfies both the given equations. Hence, the system is consistent. Geometrically, the above two equations represent two lines which are not parallel, and therefore, they must intersect. The point xy equal to 21 minus 12 is the unique point of intersection of these lines. Note that here the solution is unique. In general, we have m equations in n variables, which can be written as the matrix A I j multiplied by the column vector x1, x2 up to xn is equal to the column vector b1, b2, bm. That is same as Ax equal to b where A equal to Aij, x equal to column vector x1, x2 up to xn, and B is equal to B1, B2 up to Bm. Or if we prefer, we may also write these equations as x1 into the first column vector a11, a21 up to am1 plus x2 into a12, a22 up to am2 plus up to xn into a1n, a2n up to amn equal to the column vector b1, b2 up to bm, which is equal to x1 into a1 plus x2 into a2 plus xn into an, which is equal to b. Here ai equal to the column vector a1i, a2i up to ami. For I equal to 1, 2 up to n are the column vectors of the matrix. We also wish to inform a nice result, which means that a system of equations Ax equal to b has a solution if and only if the rank of m by n matrix A and the rank of augmented m by n plus 1 matrix AB are equal. That is, in other words, a system of equations Ax equal to b has a solution if and only if rank of A is equal to rank of A comma b. When m equal to n, the system of equations Ax equal to b has a unique solution if the square matrix A is non-singular. In this case, inverse of A exists and the unique solution is given by x equal to A inverse b. Example, we shall solve y plus z equal to 2, x plus z equal to 2, x plus y equal to 2. The system can be written in the form the matrix 0, 1, 1, 1, 0, 1, 1, 1, 0 multiplied by the column vector x, y, z equal to 2, 2, 2. Here one can check that determinant of A is equal to 2. Hence, the matrix is non-singular and therefore invertible. The inverse is given by A inverse is equal to 1/2 adjoint of the matrix 0, 1, 1, 1, 0, 1, 1, 1, 0, which is same as 1/2 transpose of the matrix -1, 1, 1, 1, -1, 1, 1, 1, -1, which is equal to the matrix -1/2, 1/2, 1/2, 1/2, -1/2, 1/2, 1/2, 1/2, -1/2. Hence, the column vector x, y, z is equal to A inverse multiplied by B, which is equal to the previously calculated matrix A inverse multiplied by 2, 2, 2, which is equal to 1, 1, 1. Thus, x, y, z equal to 1, 1, 1 is the unique solution. When n is greater than m, in general the system is underdetermined, and by elementary row and column operations, m of the variables of the solutions can be described in terms of the remaining n minus m variables. Example, suppose we are given that x minus y plus z equal to 1 and x plus y plus z equal to 1. Then we have the number of variables n equal to 3, which is greater than 2, which is m, the number of equations. One immediately finds the infinite number of solutions as the set of the elements x, 0, 1 minus x, where x is in R, or The set consisting of 1 minus z, 0, z, z is in R. When n is less than m, in general the system is overdetermined and there is no solution. Example, suppose x plus y equal to 2, x minus y equal to 2 and 2x plus y equal to 3. Then we have the number of variables n equal to 2, which is strictly less than 3, which is equal to m. The number of equations. One immediately observes that the first two equations give unique solution as x equal to 2 and y equal to 0. But these values do not satisfy the third equation. Hence, the system is inconsistent. Application. Suppose in a market there are n commodities. The price of ith commodity is Pi. Moreover, demand and supply of ith commodity are linear functions given by q di equal to ai 0 plus ai 1 into p 1 plus up to ai n p n and q s I equal to b I 0 plus b I 1 into p 1 plus up to b I n p n. The market equilibrium demands that there is no excess demand, that is E I, which is identically equal to q d I minus q s I equal to 0. This leads to system of linear equations for the variables p 1, p 2 up to p n. This system of equations can be solved by the methods described in this module. Now, let us summarize the topics that we have gone through. Through appropriate examples of matrices, we concluded that unlike in case of real numbers, matrix multiplication is not commutative, and also we have seen that product of two matrices may be a zero matrix without any of the matrix being a zero matrix. Similarly, cancellation law also does not hold, is shown by appropriate example. We then have covered the discussion on determinant, adjoint and inverse of a matrix. We have profusely illustrated our discussion through examples. We then return to the thing with which we started our study of matrices, namely two simultaneous linear equations. Here also we considered several simple examples to illustrate the points that we make. As an illustration of application, we have considered multi-commodity linear model and discussed how solution to market equilibrium of these commodities can be achieved through solving simultaneous linear equations.